So we're going to talk about something today that is really, really, really important, and really will. You'll see that it leads into the entire rest of the calculus part of this course. I wish we could have gotten to it yesterday. We just barely ran out of time. It's kind of you'll see it's kind of a long conversation. So that's why we couldn't even get it started yesterday. But really, the whole thing about yesterday was leading up to what we're going to talk about right now. And we're going to look at a little demo and use the demo to visualize and think about this stuff. But yesterday, we introduced the idea of finding an expression for the limit of a function at any value. And this was the one that we did, I think. And we found that the expression for the limit, now whether you use last semester's version or this semester's version, you'd get the same thing, but you get an expression that was this. Do you remember this example from yesterday? And then we subbed in 3 values to find the slope of the tangent of this function at those values. I believe they were 4 and 2 and 0. And we got 3 slopes of tangents. Remember this? Anybody remember this? Yes? No? Okay. And we called that the derivative. And I said that's kind of an important, like you can tell that's important because the next unit of the course is called derivatives, and everything we do in the rest of the course is all about derivatives. So it's important. But the one thing we didn't get to is how. I mean, look at it. That's the derivative. 2x minus 4 is the derivative. That is a function, right? The derivative of a function is a function in and of itself. And why is that useful? Because we know things about functions. I mean, in this case, the original function was a quadratic. We know a lot about those. And the derivative function is linear. We know a lot about those. And it turns out that the derivative function, or the derivative of a function, tells us a lot about the original function. But it has properties in and of itself. And we can analyze the derivative as a function and think about its properties. It has continuity. It has a domain, a range. It is sometimes increasing, sometimes decreasing. It has turning points. It has intercepts. It is sometimes positive. It is sometimes negative. What are all the other properties? It depends on the kind of function you're talking about. Asymptotes, all these end behaviors, all these different things that functions have, while derivatives are functions, so they have those properties too. And that tells us about the original function. Okay, so I want you to take a look at this. I want you to put your pencil down and watch. This is important. Now take a look. This is not the same function that we were looking at before, but this is a parabola, so it's similar. This is the graph. This is the equation of the original function. And there's the graph of it, obviously. And this is the equation of the derivative. It even says right there, derivative of f. This program is called Geogebra. If you had me last semester, then you've seen this a lot. If you haven't had me, you may not have seen it that much. You've probably heard of Desmos as well. Desmos is great. Geogebra is better, especially if you're programming and you know how to use it. It is so powerful. If you are doing anything in the STEM field in university or doing any computer programming or anything like that, and you have to do graphs, like, check this out. It's really, really, really powerful. I can't stress that enough. Anyway, so I love it. I use it all the time. So this is x squared, and the derivative of x squared turns out is 2x. And the derivative, and notice that when we did it yesterday, the original function was quadratic and the derivative was linear, and this one's the same way. Turns out that's a common relationship. We'll talk about that at the end of this lesson, actually. Okay, And so we're going to just kind of, and this is a point on the original graph. And watch what happens as I move the point. You can see that this line is a tangent to the original function at that point. This is what GeoGebra can do. Okay? And what is happening to this value? Well, this point is obviously a point on the derivative function. It shares the same x value. So look at that's 1.59 x value and 1.59 x value. And that's programmed into the way that this has been designed. Okay? So this will always share the same x value as I drag this around. So just, if you can make the connection today, and I think most of you will, this is big. This is a really big visualization on like everything that we're going to do for the rest of the calculus course. A lot of it involves heavy algebra as well, but the understanding lies right here. What's happening? What's the connection between this point that I'm dragging back and forth and the point that shares the x value on the derivative function? So I'm going to ask you this. We're going to break that question up into two parts. What's happening to the slope as I'll start here, and I'm going to drag the point up, or drag it to the right, which will take it up the parabola. What's happening to the slope of the tangent? It's increasing. It got steeper. The slope increased in value. And in fact, you can see the slope right there. So it's about 4 here, and it's about 1.25 there. What's happening to the point on the derivative function as that occurs? Daniel? The what about the point?
It's the same slope.
Yeah. And what of the point? I know that's what you're saying, but specifically the
y value.
Very good. The y value of this point, and this is what we did yesterday when we subbed in to the derivative to this thing, right? We found the y value when we subbed in 4 for x in the derivative was the slope of the tangent at 4 of the original function. That's all we're seeing here. But as the tangent gets steeper, the point on the function, the y value, the point is getting higher. The y value is increasing. Very good. Watch what happens when I go around the vertex. Watch what happens to the point on the derivative. I know it's subtle and maybe it's obvious, but what happened there? To me, it's worth mentioning, even though maybe to some of you, or maybe not, the specifics are obvious. So what is true of the slope of the tangent now? It's negative, exactly. And what is true of the point on the derivative function? The y value is negative. It's below the x-axis. When I go back to this side, it's above the x-axis. What is happening? What's the property of the derivative function when I'm going around the vertex? And what do we call that? Don't we call that an x-intercept? So the derivative has an x-intercept when the slope is changing from positive to negative. And that's the vertex of the parabola, which is kind of an important point of the parabola, isn't it? And so what happens, what is true of the slope of the tangent at the vertex? It's 0. And the y value is 0. That's an x-intercept. That's not a coincidence, right? That's obviously, when you think about this stuff, that's by design. Very interesting. Okay, let's take a look at a new kind of function. So what is this? This is cubic. This is a cubic function. And again, it has a positive slope. But what happens there at that cubic twist? The slope is 0. And we have an x-intercept. But what happens when I go to the other side? Now, the original function is in the negatives. but the slope of the tangent is still positive. And so that point has to go back up, and now we have a parabola. And that all makes sense, Daniel?
Sorry to be like a little bit far in the future, but is this how we find local limits? We're finding the x-intercept of the derivative?
Local max and mins kind of thing? Is that what you mean? Exactly.
Okay.
Yeah. Exactly. Okay, so cubic function, the derivative of a cubic function is a parabola, and we can see it has these same, and as I go up, as like if I imagine taking this point and drag it way up, I mean, it's just going to get steeper and steeper and steeper and steeper. So what's the end behavior of that? It's going off to infinity. So see what I mean? The properties of the derivative inform us about things that are happening with the original function. Let's take a look at some different types. This one's interesting. What's happening here? So what kind of function is this, the original function? Absolute value, it looks like. And what is the slope? Any point on this right side of the graph. What's the slope? It's just 1. So what's happening here? It's just a horizontal line at 1. But what happens when I jump to the other side? It becomes -1. And so the derivative function jumps to -1. And so we actually have the derivative of an absolute value function would have to be some kind of piecewise function, right? It actually can have an equation. You can see it right there. But it has a jump in the graph, and it has a hole in the graph. It won't exist there. There is no slope of the tangent at that point. There isn't one. And the derivative has no value there. Possibly. I don't think you were supposed to do question 4 yesterday. So, yes, today this is a big part of what we're talking about relates to that. Yeah. Okay, take a look at another one. This one's just a straight line. Whoa, where'd that point go? This one's a straight line. So anywhere on this line, the slope is the same. Look at this. The equation of this line is 2x. So the slope is always 2. We know that from grade 9. So the derivative function is just y equals 2. It's a horizontal line. It's always 2. Square root function. So what's happening with the square root function as I approach the beginning, where it starts? What's happening to the slope of the tangent? Steep. How steep? Yeah, infinitely steep. When it gets around to that point, it's going to be infinitely steep. What do we call the slope of that a vertical line? Back from grade 9. Undefined, right? Vertical lines have slopes that are undefined. They don't exist. We use the word undefined to talk about them, but you can't do 1 divided by 0. That's undefined. And so what's happening to the derivative function? It's getting infinitely large, but what do we call the property that's occurring in the derivative function? It's an asymptote. So the derivative has an asymptote where this one is getting infinitely large. And what's happening here as I go this way, while the square root function, the slope will continue to get smaller and smaller and smaller and smaller, less steep and less steep and less steep. It'll never be 0, but I suppose it's sort of approaching 0. So this is like a horizontal asymptote down there. Okay, interesting. This one's good. So this is a rational function of 1 over x. And this slope is negative. And it's approaching 0 if I go that way. So we see a horizontal asymptote down here. And it's, again, approaching infinity, the slope of the tangent as I go up here. But the slope is negative. So this is a horizontal or a vertical asymptote, but it's approaching negative infinity as it approaches the asymptote. We talked a lot about that, behavior around asymptotes. What happens when I jump over here? The slope is still negative, right? So the function is still negative. Remember there were those functions last semester where we talked about increasing and decreasing. and it's decreasing here, and then it doesn't exist, and then it's decreasing again. And so its derivative is always negative, always below the x-axis, has no x-intercepts. So like when we're talking about positivity and negativity, when the intervals of being positive and the intervals of being negative, intervals of increasing, intervals of decreasing, the slope being positive, the slope being negative, like these are all related properties between original functions and their derivatives. This might be our last one. So this is the equation of this graph, the original function, is x to the 1/3, the cube root of x. It has a bit of a different kind of a graph. It's like a cubic, it's like x cubed, but lying on its side, because it's kind of like x equals y cubed, right? So it has a very shallow slope if I go this way, but again, it is approaching infinity and then goes around and is still positive. So this graph looks a lot like the last one, but it's always positive. But again, it has that asymptote that it approaches and goes to positive infinity from both sides. But the whole point here is derivative is a function. We call it the derivative function. It has properties. It can look like all the functions we looked at in the last unit, or last course, sorry. And we can analyze it and use its properties to tell us other things about the original function as well as properties about itself if that happens to be useful. Very, very cool. Now, one of the things that we noticed in that we're kind of is what we're talking about today. And then, but we won't really use this idea of what we're talking about today until, well, not really even the next unit, but the unit after, okay? But is what happens when the limit at a particular point doesn't exist. Well, this statement right here, or we could write it this way, right? I don't know why it's written this way. Could be both, doesn't matter. If this doesn't exist, well, this is the derivative. This is the definition of the derivative. So that's why it says f prime at a, like the derivative at a. If the limit at a doesn't exist, the derivative doesn't exist. If the derivative doesn't exist, the original function has no slope at that point. Now, if, I'm going to say the derivative does not exist. If the derivative does exist at x equals a, then we say, whoops, f at x is differentiable at x equals a. Some functions will be differentiable everywhere. Their derivative will exist everywhere. I mean, think about what was the derivative of the parabola? It was linear. Linear, what's the domain of a linear function? They exist everywhere. That means the original function is differentiable everywhere. And we're not going to get this today, but again, where the derivative does not exist turns out to be an important thing to know. That's going to help us in what we're going to do later on. Okay? But all we're going to look at today is the kinds of times when the derivative won't exist. And you can think of this as when the limit doesn't exist. Any questions on any of that? So what we're going to talk about now, if the function doesn't exist, then the derivative is not going to exist. Like that is clear. So square root function doesn't exist everywhere, right? The y equals the square root of x, just the basic one, only exists for x greater than or equal to 0. So any negative values of x, the derivative won't exist because the function doesn't exist. So we're only talking about examples of functions that have values at x equals a, but the derivative does not exist at a. The function exists at a, but the derivative does not exist at a. So the first one is called Cusp. Or you could think of it as pointy parts. That's not an official term. They're actually called cusps, or a point. So what graph did we already see that has a point? Very good. So if I have an absolute value graph, it exists at A, but the derivative at A does not exist. And this is f at x, right? That graph is f at x. Its derivative doesn't exist. It has no slope at A. Okay? Another one that is a cusp looks like this. It curves and points and then curves off again. So different from like a smooth curve that you might see in a quartic function. It's not like that. I'm going to draw this again because that wasn't very good. It's more, it's a hard turn. Okay. And again, this is f at x. It exists. The function exists at A. F at A does not exist. Next one. Everybody get that okay? Vertical tangent line is the next one. And we talked about this. This is where the slope is undefined. Slope. And the graph we looked at was like this, like a cubic lying on its side. So this is A. It's not an asymptote. It's a vertical tangent line. It has a slope that's undefined. The function exists there. So this is what's a little bit tricky. Like we can think of it as having a tangent line. The tangent line is vertical. But the slope has no value because the value is undefined. So it doesn't have a slope, but it has a tangent line. And that's just a subtlety that won't really apply to us much, but some people might wonder about. A couple more, everybody okay? An endpoint, this one's sort of like along the same lines. Now the endpoint that we're going to look at is for a square root function. Whoops, that was pretty bad. Okay, so square root function, that's also pretty bad. So here's a. The function exists at a, but the derivative doesn't exist. And because the derivative, the definition of the derivative comes from a limit. Well, the limit can't exist because it has no left-hand limit, this one in particular. So if the limit doesn't exist, the derivative doesn't exist. That limit is the definition of a derivative. And again, you would think of this one as having a vertical tangent line at that point, but any graph that has an end point, the derivative does not exist at that point because the limit doesn't exist. It can't. And then finally, sort of for the same reason, sort of similarly, if you have a break, and again, the break, it's only relevant if the function exists at the break. So it does exist. This one's got a closed point there, closed circle, so it exists. Because again, if the function doesn't exist, it's relatively meaningless to say that the derivative doesn't exist. It's a given. But if the function does exist and it's a break, the derivative will not exist because left-hand limit doesn't equal the right-hand limit. Limit does not exist, so it can't exist. So this idea of differentiability, we're going to see its implication later. Turns out it's important. Yes? Other graphs could have endpoints and not be a vertical tangent line. Off the top of my head, let me think. I mean, if you restricted the domain of any function, it would have a place where it starts. So, right? I don't think any others that we have talked about have natural endpoints. Oh, no, logarithms have asymptotes. But there are other functions that have places where they start. And it doesn't have to be at a vertical tangent line. Okay. This doesn't really have anything to do with what we're doing today. It's just more practice. It's very similar to the learning goal that we did. So let's try this one. It's a bit harder. You may have found that because it's in a different form. It's in vertex form. Again, whenever you're asked to find the general derivative, you're supposed to use x, as h, not the x approaches a, the h approaches 0 version. So f at x plus h is x plus h plus 1 squared minus 3. And be careful when you're subtracting f at x, you got to subtract the whole thing. Remember, what has to happen is all the constants have to be gone so we can get a common factor of x, right? And if I didn't subtract this whole thing, that wouldn't happen. I don't think it's the same, it's similar. Yeah, so it's very similar. Now you might not need my help, so you can go ahead and just do this if you like. The reason why this is a bit trickier is expanding this trinomial squared is going to be a little bit harder. So if you want some help doing that, I can help you. I would just look at it as like, so it's going to be x times x, which is x squared, and then x times h, and then x times 1, and then h times x, h times h times 1, and then 1 times x, 1 times h, 1 times 1. Minus 3 minus, I'm going to expand this bracket, and then plus 3. Whew. And if you want to see what happens here, anything that doesn't have an x, or doesn't have an h, sorry, has got to be gone. So we can common factor. Like I know that's got to happen at this step. So I've got the 3 and the negative 3, and the 1 and the negative 1. I've got 2x minus 2x, and I've got x squared minus x squared. So again, it looks like what I got is correct. Every year, some people, it's great that you know that's supposed to happen, but you do the algebra wrong, and so it doesn't actually work out, and then in the next step, you just like get rid of all of them, even though they didn't add or subtract, and you know, you get busted. Okay, everybody okay with that? Okay. We got one more thing to look at here. I'm not really sure if you have to write all of this down. I mean, you can if you want. We're going to do one more example. You definitely don't have to write that down. So what we talked a lot about today is how the derivative of a function is a function in itself. It has properties that we can analyze, and some of those properties tell us really important things about the original function. And so they're closely related. The derivative and the function are closely related. And for polynomials, there's a really nice, simple thing that happens where if your function f at x is polynomial and it's of degree n, The derivative will also be a polynomial for sure, and will be degree n minus 1. So when you take the derivative of a polynomial, and we don't talk about degrees of other things. In rational functions, we talk about the degree of the numerator and the degree of the denominator, but we don't talk about the degree overall, right? So we only talk about degree of a polynomial function. The degree will always drop by 1. So if f of x is cubic, that's degree 3. So f prime will be degree 2, which is quadratic, and we saw an example of that. If f of x is quadratic, that's degree 2. F prime will be degree 1. We saw a bunch of those. Linear. If f of x is linear, that's degree 1. F prime will be degree 0. What's degree 0? That doesn't, yeah. It's a constant. It'll be a horizontal line. If f of x is a constant, that's degree 0. F prime will be equal to 0. It'll have no slope. Slope will be 0, which has no degree, actually. It's not negative 1. In the end, that's not really a big deal, but anyway. Okay, so that is good. Turns out that's going to be really important, and that's going to be something we're going to get see a lot more in the next unit. We're going to talk about derivatives of polynomial functions and derivatives of other kinds of things as well. Okay, last thing we're going to do, you do not have to write this down. I'd rather you just kind of watch. I don't see any point in writing this down. You can write it down later if you really, really want. This is just kind of interesting because this should be easy, but I don't know that it is. In Unit 3 of Advanced Functions, we talk about the definition of a polynomial. You probably don't remember the official definition, but out of these 6, which ones are polynomial, which ones are not, and why not? Because a lot of them are written to look like polynomials, but they might not be. What about that first one? Do you think it's a polynomial or not? Seema, no? Why? Just say why you think it's not. Yeah, negative in the exponent. And that's exactly right. Polynomials have to have positive integer exponents. This would be 1 over x squared plus 3x plus 5. So that's going to be a rational function. So this is definitely not a polynomial. What about f of x equals 17? No? Why not? It's hard. This is harder than you think, right? It's just second guessing yourself. What do you think? What does anybody else think then? It's not just a point. Yeah, we just looked at that. It's a constant, and we just saw that it is. That is a polynomial. We had it right there. If f of x is a constant, that counts as a polynomial. So it turns out that does count as degree 0. It's a polynomial. So that one's fine. 3 to the x minus 4. What kind of function is that? What do we call that? Exponential. So this one is not because it's exponential. What about x to the 1/2 plus 7? Or x to the 0.5 plus 7? What do we call that kind of a function? Yeah, that's a square root function. That's square root of x plus 7. That's not a polynomial. What about the next one? Yep, you're right. It's 1 over 4x squared plus 3 over 4x plus 5 over 4. That sure looks like a quadratic to me. No, nothing ever said that they have to have integer coefficients. Isn't that, this is hard, isn't it? And then the last one is not, it's rational. When you have x in the denominator, that's a negative exponent on the x. That's when you can't. Over 4, this is written to not look like a polynomial, but it is. This is the type that's actually not a polynomial. Okay, the worksheet that was posted yesterday, the rest of it is your practice for today. Any other questions or comments?